Thank you, Tori. Well, this new model is very exciting in many respects because it ties together a lot of loose ends from Europa studies that have spanned most of the last decade. Here in the first slide, I'm showing a figure that represents two previous models for Europa's shell. The one on the left shows the ocean and the ice shell. The total thickness of this is about 150 kilometers. But here the shell is depicted as being very thin, maybe only 5 kilometers or less. And the plumes that you're seeing here would be in the ocean. They're hydrothermal plumes from the floor, from where the ocean floor meets the mantle of Europa. On the right-hand side is a depiction of a thicker shell model, where the shell here would be about 15 to 30 kilometers. It's not quite to scale. But the underlying plumes from the ocean floor would impinge on the bottom of the ice shell and would warm it, and as such would create plumes within the shell. These are convective plumes, so it's actually solid material that is mobilized because it's slightly warmer than the surrounding. So similar to what you would see in a saucepan of bubbling soup. I'm told miso soup does this very well. But you can see different convection cells, and material moves upwards in the center and down at the margins. And these two models have been used to explain some of the observations we've seen on the surface of Europa. But neither of them have been able to explain everything we see, and that's been a big problem for us. But with the new model that Brittany and her colleagues have put together, we can now explain pretty much every geological observation that we see surrounding chaos on Europa. So it's really sort of come along and joined together a lot of dots. So we're very happy to see that. Next, I want to talk about the distribution of chaos and its age. If you look at this image of Europa, you can see that the surface looks very different from, say, the surface of the Moon or Mercury. Those bodies are very heavily impact cratered. They've got a lot of cratering scars on them, whereas Europa, you can see, has hardly any. In fact, I'm not sure you can even make any out at this scale. Now, we use the number of impact craters on the surface of a body as a proxy for age. We assume that things like comets and meteorites that are coming into a system impact the surface on a fairly constant basis. And so if something has a lot of them, that means that it's been sitting there getting this weathering process for a very long time. Whereas if something doesn't have many craters, it's probably very young. And in the case of Europa, something has happened to erase the impact scars from the surface. And in this case, it could be tectonic features, so faults and fractures on the surface that could erase whatever has come before. It could be some kind of cryovolcanism, and it certainly could be chaos. So if we can start the movie, please. And in fact, the average age of Europa is thought to only be about 60 million years. Now, on human timescales, that's a very long time, but in geological timescales, that's a blink of an eye. It was almost born yesterday on the surface. So Europa already has a very young surface age. And here we're zooming into Thera macula on the left, which Brittany talked about earlier, and a chaos very close to it, Thrace macula on the right. As you can see, they're both quite large. Thera is about 80 kilometers, maybe a little over 50 miles across. And notice that these are very different from their surroundings. They're both very dark. They have unusual scalloped margins. They don't look like a lot of the long linear features that we see that appear to be faults and fractures. These two arrows are pointing towards a semicircular fracture system that was once intact. We're looking at the two sides of it, and you can see that Thrace macula on the right has actually disrupted the middle of that. It's completely destroyed it, in fact. And so this shows that this chaos region overlies those tectonic features, and so it's much younger. So what we're showing here is not only is Europa's surface young, but chaos is very young still, and in fact it's one of the youngest feature types, if not the major young landform on the surface. So it's very, very young. Here I'm just zooming out, showing you the equator. There's a big X just off the center to the left. Just to the south of that is Connemara chaos, which Brittany also mentioned earlier. You can see all this brown mottled material over the surface. All of that is chaos terrain. It's very widespread. In fact, we think, estimates vary because we don't have particularly good imaging data of much of Europa, but we think it could be as much as 50% of the surface has been completely destroyed in recent times by this chaos formation. And so to summarize, this is a very important result because, first of all, it draws together many of the conflicting observations that we've seen in the last 10 years. But secondly, it shows that there could be these huge hidden lakes in Europa's shell, widespread bodies of water, maybe taking up as much as half of the upper shell of Europa. And so chaos regions are going to be extremely important as possible future targets for exploration. And with that, I'll pass back to Dwayne. Thank you.
Thank you all. So